Hey y'all, my name is Zach Williams. I'm with Dr. Negar Mehr at the University of Illinois Urbana-Champaign. And I'm going to talk about our paper, Distributed Potential iLQR, Scalable Game-Theoretic Trajectory Planning for Multi-Agent Interactions. So in many different robotic applications, we have a series of robots, and they're trying to compute some control input to get somewhere or to achieve some goal or to lift some object. So across all these different things, whether that be autonomous driving or warehouse automation, space robotics, you name it, the common thread is that agents must interact with each other in a scalable manner. And this is kind of the main aspect of our contribution that I would like to talk about. So thinking about multi-agent planning, we can formulate this as a dynamic game. So we have agents here, say they're trying to get to some goal over here. And say you can model this as a dynamical system where for an agent I has some say xi and some dynamical model fi. It also has some cost function ji as a function of all the states of each agent. And so trying to see what the outcome of such a problem would look like, we bring in the notion of a Nash equilibrium. And the basic idea here is that given that other agents are acting optimally, given u minus I star, I myself as agent I have no incentive of deviating from my optimal control ui star, and treating this across all agents unilaterally, we have a coupled optimal control problem that we'd like to solve. And this is not an easy task. So from prior work, we have leveraged the certain structure in multi-agent interactions, namely for symmetric interactions, we bring in the notion of a potential dynamic game, where instead of having to solve this coupled optimization problem, we're solving this single agent optimization problem, where we have this potential function p of xu. And this is all fine and great, but the issue here is that this is a centralized approach. We are accounting for the states and controls of all agents at all times. And this doesn't really scale well to larger problems. So stepping back a little bit, as I'm walking through a crowd, just intuitively, I'm not really paying attention to everybody else. I'm really only paying attention to the people in front of me who I might walk into, or people I'm trying to cross paths with, people who I can directly see who have an impact on my planning problem. And similarly in the robotics case, as agent I don't necessarily care about all the other agents in my observation space. I really only care about the agents who might directly come in contact with, who are in some subset of what I can see. Similarly for agent 2, it really only cares about its neighbors. It doesn't really care about what's going on over here in Antarctica. And so with this is kind of the key insight to our approach. We are taking advantage of the sparsity in the interactions to make the problem local, to sparsify the centralized problem. And so here I'm plotting quote unquote agents in Brownian motion just to show how the interaction graph is formulated in the centralized case on the left versus the distributed case on the right. And so you can see as time progresses, the centralized case is looking really messy as it's trying to account for all the different impacts of the interactions as time progresses, regardless of where they are. Whereas in the distributed case, you can see how as the agents are moving around each other, the interaction graph is kind of mutating as to account for the locations and the impacts of agents as time progresses, given where they are. So they're really only accounting for the agents in their subproblem, this ni, this j and ni here. And so pairing this with a trajectory optimization algorithm, potential iLQR, multiple agents, we can solve this problem and show that it produces intuitive trajectories here, where here I'm just using unicycle dynamics in 2 dimensions. And quantitatively, we can show that the solve times for both of the algorithms across different dynamical models, as well as across different scales of number of agents. And as you can see, as you scale up the number of agents here, the distributed variant in the green consistently outperforms the centralized variant in the blue as expected. Since it's not having to solve this huge problem here, it's solving this local problem specific to that agent. So looking at this on hardware, we've also shown that it's able to generate intuitive trajectories using 5 crazy flies as they navigate around each other in our lab here. And you can see that as the 2 groupings of agents here are only solving their own subproblems, they're able to scale up to these 5 numbers of agents as they navigate around each other here in the lab. And so in summary, we've enabled game-theoretic trajectory planning in a scalable fashion. And we've done this using both the concept of the potential game as well as the sparsity of the interactions to bring this big centralized problem into a smaller local problem. And so with that, I'd like to thank you for your time, and I look forward to seeing everybody in London. Thank you.